So, so any questions that people have, they can ask them at the end of each little short section as well.
Okay, so we'll answer the question at the end of the slides.
Yeah.
And okay, perfect.
Okay, we are.
That way things are fresh for them as well.
Yeah, thank you.
Okay.
We are live and recorded.
Okay, very good.
So let's get started.
Okay. Well, thank you very much for the invitation, and thank you to Mohammed Mansour for seeking me out and asking me to do this. I have done this sort of style of thing a couple of times before, so hopefully this will go fairly smoothly. So I'm going to give a sort of a run through on seismic inversion.
Actually, can you just give me just a few seconds to introduce you?
Of course.
Thank you for accepting this invitation as well. And we appreciate it the first time to get the Amal program this valuable session. And I think all people are waiting for this session to be out. By the way, I worked with actually closely in UK, and was one of the best in geoscience and geostatistics. Actually, is managing director for Wessex Geoscience Ltd, and having co-founded this company with Mr. Julia Francis in 2022. And he is a geophysicist and geostatistical whose career over 30 years, I think, actually, or more.
It's more, actually, 45 years now.
45 years, yeah. With exploration and development, production geophysics. And actually, I think you are the consultant that using sector subsurface definition and uncertainty as well.
Okay.
And if you have any further introduction for yourself, that would be great adding value.
Okay.
On behalf of Amal Management and EGS, we would like to thank you for accepting this session, and good luck with this tonight's session. Thank you.
Okay, thank you. Well, yeah, I have a background in seismic inversion and QI work.
So the floor is yours now.
Thank you. So I have a background in seismic QI work and seismic inversion. I've done a lot of technical work over the years. I do some expert work as well. And I have, once upon a time, I did work in an oil company a long time ago as well. So I'm going to take you through a very quick tour from some very basic fundamentals with a little bit of maths, which I'm sure the engineers will have no trouble with, and the geophysicists. Some others may have some problems, but then we'll move on to things that are more pragmatic and practical. So I'm just going to start with a very quick introduction to give you sort of an overview of where we're coming from and try and keep this quite simple. So what I'm mostly going to refer to as seismic data, of course. And I mean, we kind of know, and most of us know, that seismic reflections occur from boundaries between layers in the earth of differing properties. That's how we see things, they're contrast. And what seismic is actually sensitive to is the rock property, which we call impedance, which is a velocity of some sort multiplied by the bulk density. Now, the reflection amplitude that we see, the strength of the reflection, is proportional to the contrast in those properties, the reflectivity. So the seismic sections that we look at and we use every day in 3D seismic is our approximate measurement of the Earth's reflectivity, but it's been convolved with some kind of input signal, which we call a wavelet. And this leads us on to what we call the convolutional model. So all of this is kind of how we see the Earth and our recordings of reflections from layers within the Earth. What seismic inversion is trying to do is to reverse that process and get us back to thinking about the layers themselves. So on the left, I'm showing you here an impedance profile in depth or time. So this is hard here, softer below, medium above. And then at each boundary, there will be a reflectivity, a reflection coefficient. And we pass a wavelet along past that. And we then end up with spikes that are convolved with scaled versions of that wavelet. And they change sign according to the polarities that we see over here. So we can define the reflectivity from our impedance, which is the density multiplied by the velocity. So the impedance, sometimes referred to as IP, because this is the normal or P wave impedance. So this is simply the multiplication of the sonic log, dt, with the density log. The reflection coefficient, so those reflections between boundaries are in fact based on this relation contrast between the boundary properties. So it's the second impedance minus the first one divided by the sum of the two. That's how strong the reflection will be. We can also define another way of propagating waves in the Earth, shear waves. And shear waves, we can define a shear impedance as bed density times the shear velocity. And obviously we do also record shear sonic logs as well. So we can see straight away that we've got some very simple terms here to think about in terms of inversion. We've got the P wave impedance, the shear wave impedance, and then the strength of the reflection coefficient between the two. And later on, I'm going to link the reflectivity and these two together when we look at pre-stack inversion. So normal incidence, when the wave comes down and comes 90 degrees and reflects straight back, we get this response with this equation. If there is an angle involved, so we're now thinking about pre-stack, if there's an angle of incidence involved, we're now talking about AVO type properties, amplitude variations with angle or offset. Then we get a relation here I've shown very general called elastic impedance, which is a combination of P wave velocity, shear wave velocity, and the density. It includes the angle of incidence. This is now thinking about pre-stack size. We get a little bit more information. So we've got the angle of incidence here across our pre-stack data, and we have a constant thrown in here, K. K is the ratio of the shear velocity to the P wave velocity, and that comes up a lot in equations related to seismic impedance. So we've got elastic impedance as a very general statement about angles and reflectivity being converted into impedances. So what is the objective or the goal of seismic inversion? So we can think about making a synthetic seismogram. We do this with well logs very commonly. So if we do that, we're computing what we think the seismic response would look like by forward modeling from our well logs. So if we assume a convolutional model, so a convolutional model is we generate the reflectivity in time, we convolve it with a wavelet, then we get the synthetic seismic trace in time. So how would we go about that for a synthetic seismogram? Well, we would take our depth domain measured logs and we'd integrate them to the time domain. We'd compute the impedance from the velocity log, the sonic log, and the density log. We then calculate reflection coefficients between each sample down the log, and then convolve that with a wavelet. And this would give us a synthetic seismogram. So what is inversion trying to do? It's trying to reverse this process. And in principle, the idea would be to create a depth model of velocity and density from our measured seismic traces. Now, as we're going to see, we can't actually do this. So there are lots of things we try and approximate to help us do it, but we can't actually achieve this. But we can get some way along the reversal of this process. So forward modeling, sonic and density logs, depth to time, compute reflectivity, bring in our wavelet and convolve, and we get what we think of as a seismic trace. Now, if we take the real seismic trace and we try and reverse this process, what happens? Well, what happens is we get partway back, we sort of get somewhere about here, and things start to go a little bit wrong, and we start to make assumptions then that actually become part of our answer rather than just being pure data from the seismic. And we'll come back to those in a moment. So there are other aspects to think about when we're thinking about inversion in general. So we could think about just normal stack seismic, and we could sort of talk about inverting that and get some kind of impedance from it, some kind of rock property from it. But we also have to be aware that there are different seismic responses depending on whether the layers we're looking at are thick layers, in which case the amplitude responds to the layer properties quite nicely, or whether we have thin bedded layers where the amplitude responds but with a tuning effect which compromises our ability to see detail, or it may be that we've got stacked thin beds. And so then the amplitude responds to what we call the effective properties. So we can still see average effective properties, but we only see the average of the whole thing. We don't see the individual thin layer properties. Then also we've got the case where AVO effects, offset amplitude dependency on offset effects predominate. And in that case, we might think that acoustic impedance is not sufficient. So the simplest form is not sufficient. And so that might lead us to either AVO studies, which can be classified as a form of inversion, or a more general case of that would be what we call extended elastic impedance, which is a very general case incorporating the same maths as we see in AVO studies. So thick bed, so this means probably greater than about the wavelength divided by 2, so quite thick. Thin beds are when we're down at about lambda over 4, wavelength over 4. So these are typical where we get brightening due to tuning and things like that, or anything that's a little bit thinner than that. And then stacked thin beds, where we see layer effective properties rather than individual properties. So what is seismic inversion then? What are we trying to achieve? So we view the seismic trace as being a bandpass filtered reflectivity of the Earth. And in fact, all we've got to do to convert seismic reflectivity to an impedance, a basic impedance, is sum up the amplitudes down the trace. Mathematically, summation of the reflectivity down the trace is what we call integration. Mathematically, that's just an integration. So the integration of a seismic reflectivity trace gives us a bandpass filtered seismic impedance. That's really all it is. And there's lots of other sophisticated things that we throw on top of this, but fundamentally, seismic inversion is basically just the integration of a seismic reflectivity trace. That would at least get us to what we call relative impedance. Anything beyond that, there are more complex things. We're going to go and talk about those, but that is fundamentally all that we're doing. We're just integrating seismic traces. It's an attribute, if you like, of the seismic trace. So that's just a very quick introduction as to what I'm going to go on and talk about. So if there were any questions while I'm just setting up the next presentation.
Okay, great. Till now, there is no questions, so we can move on to the next slide.
Excellent, thank you. I'm just going to make sure this comes up properly full screen. So hopefully you'll see the second part coming up now.
Yes, it's clear.
Good. Okay, so what are we trying to do in seismic inversion? We're trying to recover impedance as a function of depth or time. So mathematically, we sort of make assumptions that we've got plane parallel layers at each seismic trace, and each layer consists of constant material properties, some kind of rock property. And we invoke this convolutional model, the idea that we convolve the reflectivity with a wavelet, and that gives us what we call a seismic trace. The T here is because I'm referring to the seismic trace in the time domain. These days, it could be referred to in the depth domain, and we can flick between one and the other very easily using a velocity model, very typically on a workstation. However, one thing to bear in mind is that really inversion is properly carried out in the time domain, because if you carry it out in the depth domain, the wavelet would stretch and squeeze with the velocity model. So it's actually more convenient to carry it out in the time domain, but we can interchangeably go from one to the other. So it's not really a limitation. So RT is the reflectivity trace, and WT is our wavelet, the kind of the basic energy that's going in from our seismic source. So with our convolutional model, and we assume a layered Earth, so in a layered Earth, the reflectivity function only exists at the boundaries of the layers. Between the layers, there's no variation in property. It's a constant property between the layers. So only at boundaries do we end up with reflections. And so our seismic trace is comprised of a series of layers of which there are reflections at each boundary. So NL is the total number of layers. And in the trivial sense, you might regard every seismic sample as representing a layer almost, if you like. So if we think about impedance in any particular layer, well, the impedance in any particular layer would be the velocity times the density. The reflection coefficient at the bottom of that layer depends on the impedance contrast. So it's this equation I showed earlier, the reflectivity is the next impedance minus the current impedance divided by the sum of the two. This is the reflectivity. Now, if we want to find the impedance in a particular layer, we just rearrange this equation. And that immediately shows that we've got a bit of a problem, because when we rearrange this equation, in the equation as it is, we can isolate the reflection as a function of two impedances. But of course, what that means when we rearrange the equation is we can't isolate the impedance in a particular layer, because we always end up with it being dependent on the current layer to get the next impedance, plus this term in the brackets, which relates the reflectivity, 1 plus the reflection over 1 minus the reflection. So this isn't directly solvable, because it's always dependent as you go down the trace. So the impedance in one layer depends on the previous layer and so on. So the impedance at any particular layer is effectively the summation of all these reflection coefficient terms to get you to a particular layer. So this effectively is defining, if you like, loosely, the summation idea. In fact, it turns out you can approximate this very nicely as an integration. So as long as the reflections are very small, and in fact 0.2 is quite big actually, but as long as they're less than about 0.2, you can actually approximate the logarithm of any impedance is approximately the logarithm of a current impedance plus 2 times the sum of all the reflection coefficients to get there. So actually, this is where the summation or the integration down the seismic trace comes from. And it's a very simple relation, and it's very, very effective. So to recover the actual impedance, we need at least one other impedance, because the impedance at each layer depends on all the reflections above that layer. So we could, in theory, recover the true impedance, but as we're going to see, we can't actually do that. We can only really recover from the seismic the relative impedance, the relative change in impedance. So let's stop at that stage for a moment. Let's think about how we estimate the reflectivity itself from the seismic, because the seismic doesn't quite see reflectivity. So we can think about this problem in the frequency domain, in which case the seismic trace in the frequency domain would be the reflectivity in the frequency domain convolved with or multiplied by the wavelet in the frequency domain. This is when we start to see a limitation of trying to derive impedance from seismic. So the seismic trace here, this is the Fourier transform of the seismic in the frequency domain. This is the Fourier transform of the Earth's reflectivity. This is the Fourier transform of the wavelet. The problem is that the reflectivity of the Earth is broadband. It has every frequency in it from 0 up to infinite frequency. There's always some detail that we don't see. But the trouble is the wavelet is not broadband. The wavelet is band limited. That means we cannot recover the full reflectivity from a seismic trace, because the wavelet filters out quite a large element of it. It's not fully broadband, it's restricted in bandwidth. And because it's not broadband, it means the seismic trace is not broadband. So we're missing information. We're missing low frequency information, and we're missing high frequency information. Now, what that tells us in theory is that we want to find, in order to create reflectivity from a seismic trace, we need to get rid of the wavelet, basically. Well, to get rid of the wavelet, we would need to find the inverse operator, let's call it VT, the inverse of the wavelet, which when you convolve it with the wavelet, gives you what's known as a Dirac spike, a single reflection coefficient. Because the wavelet is band limited, there is no operator that can do this. It's impossible, because a Dirac spike has infinite bandwidth. So the wavelet is band limited. So therefore the inverse of the wavelet is never a spike. It's something that has a width. And in fact, the convolution of the inverse operator with the wavelet is an averaging function. So we don't get a spike, we get what's effectively an averaging function. This poses a limitation on everything that we can recover from a seismic trace. We don't get back reflectivity, true reflectivity, we get back average reflectivity, which means we can only recover locally averaged impedances. So this is it in a picture here. If this is our wavelet, that would be its inverse operator in the frequency domain here. And this would be our deconvolved wavelet, would be a white spectrum like this, a boxcar. But the trouble with that is it has a width, and that width poses a fundamental limit on what we can actually get back from seismic inversion. So this is just a repeat of it, just to show it in the time domain. So the seismic trace convolved with the inverse of the wavelet in theory gives us reflectivity, but it's not actually the true inverse here of what the seismic's convolved with. The true inverse of the wavelet is actually the convolution of the wavelet with this inverse is actually this averaging function. So we don't get back reflectivity, we get back the average, spatially or temporally averaged reflectivity. Now, this imposes a very classic limitation on seismic inversion, and I'm going to show it here. This is taken from one of the oldest papers on seismic inversion, and it's a paper that everyone forgets about, but it's got a very good lesson in it that everybody needs to remember with seismic inversion. This paper is by Oldenburg. It was published in 1983. So they show an impedance profile, and they show, and it's a very simple one. It doesn't even have thin beds in it, really. They show the reflectivity for it, and they show the reflectivity spectrum. They have a wavelet spectrum here in the frequency domain, and they convolve the reflectivity with the wavelet spectrum to give you band limited reflectivity. So we lose these high frequencies because the wavelet only sees this part of the Earth spectrum. So we only end up with this much. And then what happens is we revert this reflectivity. When we revert it after filtering with the wavelet, we get back to the band limited spectrum here. So you see that these are no longer spikes. They've got width. They're still all pretty much separated, but they're not spikes anymore. They're averages. But something else happens as well. When we convert this back to impedance profile, what we get is this. And what you see is that we get something called band limited impedance. And you see that not only do we get local averaging, we have also lost all of the low frequency trend that we had in the original. That's because we're actually missing low frequencies as well. So that might be what the Earth signal looked like, an increasing impedance profile. That's what you would actually recover as information from the seismic trace itself. Anything else that is added into an impedance inversion doesn't come from the seismic. This is the part that comes from the seismic, what we call the band limited impedance. And it lacks this low frequency trend, and locally it is averaged. So we can use this recursive relation. We can approximate this with this log normal transform. So how small is small for small reflectivity? Well, it turns out actually it can be quite big. So if you look at reflection coefficients here of plus or minus 0.2, that's a big reflection coefficient, actually. The error would still be well under 1% in impedance. So actually, there's not really a big issue with using this integration approximation to seismic inversion. It works absolutely fine. The errors are really tiny in any practical application. So this averaging operator that I've talked about, there are no shortcuts around this. You can't hide away from this problem. So no matter how many times people tell you that there's a way to get around this problem, there isn't. It's basic physics. You can't change the laws of physics. So the averaging operator applies to all inversion methods, including deterministic inversion methods. So they also impose restrictions on the way we tackle the problem. So typically, we might limit the layers in the solution. We limit them so as we only come out with individual layers. That's what model-based inversions do. The other way to do it is limit reflectivity coefficients, so make them sparse. That's really just the reflectivity version of limiting the layers, and this would be called sparse spike. But it doesn't really matter which way you approach the problem. The limitation is the same in either case, and the limitation is fundamentally imposed by the physics of the wavelet. Now, another point to make about this is that we can add any number of what we call spike pairs or dipoles. A dipole is a pair of spikes of equal and opposite amplitude, but they're the same amplitude. And if they're very close together, what happens if you convolve them with a wavelet is they disappear. So you can add any number of those to your inversion, and it won't make any difference to how well it matches your seismic. But of course, you can create lots of false thin layers by doing that. In all cases, when we're inverting, what we're trying to do is get what we think is the best trade-off between accuracy and resolution. Resolution means that we've got finer layers, But if we want high resolution, we have to accept that there'll be a large uncertainty. On the other hand, if we accept an answer with low resolution, we can make the uncertainty smaller. So it's always a trade-off between those two things. This is an example I always use to show this problem of the dipole, what we call the dipole annihilator. So I've shown you 3 different impedance profiles. So this is impedance going this way. This is depth or time. It doesn't really matter. What you see here, this is a hard top with a gradational base. This is a hard top with a gradational base with lots of little thin intercalated units in it. And then this is a simple average top and base. If you convert those to reflectivity, they look like this. So this one actually is a big top kick, and then it's actually decaying down here. This one has a big kick, and then you see these dipoles, pairs going down, equal and opposite polarity. And then this one here, top and a base. But here's the thing about these 3 models. When you convolve them to within a scaling coefficient, they all look the same. There is no mathematical difference between those models when you look at them on seismic. So which one do we actually invert for? Well, the one we invert for is this one, which of course is equivalent to this one, which is the blocky, thick layered model is effectively what we invert for. We can't invert for these 2 because we can't constrain them from seismic. So you can see here, they all look the same. They're basically the same answer when we see them convolved with a seismic. So this is non-uniqueness in seismic inversion. Okay, that's the end of the second section.
Okay, we have 4 questions.
Okay.
Okay, first question, Ziad says, we usually suppose in the convolutional model that the reflectivity is only non-zero at the layer boundaries, but in reality, things like attenuation and multiples affect the data. How could the convolutional model be adapted to include these effects?
Well, generally, when we're dealing with seismic inversion, we make generally the assumption that the effects of attenuation and things like that have already been compensated somewhere along the line during the seismic processing. So we're basically dealing with either a stacked section, or we're dealing with suitably prepared pre-stacked gathers, which might be several partial stacks or gathers. But the general assumption in pure inversion is that any other effects other than potentially angle dependency, what we call AVO, have already been dealt with. So they've been dealt with in the imaging process and so on. So some of these other effects really start to manifest when you start talking about the imaging. So for example, attenuation might be compensated by Q compensation down the trace, or it may be that we're dealing with velocity anisotropy and so on. But generally all these things these days are regarded as imaging considerations rather than inversion. So I'm kind of sticking to the definition of inversion being much more focused on the reflectivity rather than these other factors that obviously are very important in seismic processing.
Okay, great. Second question, when we assume a spike reflectivity model, how realistic is this assumption compared to actual subsurface geology?
Within the limitations of averaging, it's very successful. So providing we accept that we have a limitation, physical limitation imposed by the wavelet, which is that we're averaging the subsurface when we see it with seismic, beyond that, it is actually pretty successful. There are limits, and I will talk about those later on. One of those limits is things like tuning, which it doesn't handle very well, but I'm going to talk about other ways to handle tuning later on.
Okay, we have also Omar asks, what do we use dipoles for?
Sorry, say again?
What do we use dipoles for? What is the use of dipoles?
Well, I'm simply using them as a demonstration that they introduce non-uniqueness into inversion. So you don't use them in practice, but a dipole is something that vanishes when you convolve it with a wavelet. If they're close together, they would vanish. So it's a warning really to say that if you start adding lots of thin layers into your model, it's not constrained by your seismic trace. So those features just become unconstrained additions to a model. So there are occasions in stochastic inversion when you do that deliberately, but they're quite constructed quite differently. And I will refer to those a little bit later on. So they do crop up in theory in something like stochastic inversion.
Okay, Mustafa asks, how could we validate seismic inversion results if we didn't actually drill the well and got the codes?
If you've got relative impedance inversion, you don't really need to validate it because it's simply a transform of the seismic trace. If you generate a deterministic inversion, which includes perhaps seismic velocities as a low frequency constraint, then again, you might be able to make judgments about what happens maybe as you go from shallow to deep or something like that, but it does become more difficult. But certainly for a relative impedance, it's simply a trace attribute, and it's as valid as the reflectivity trace that you look at for general structural interpretation and so on.
Okay, another question. While band limited inversion only covers part of the impedance and not the full broadband response, does that mean we might lose geologically important details like thin bed or any layers boundaries? And if so, how can we reduce this loss more than band limited impedance?
So yes, you lose high frequency, so that's thin layer effects, but you also lose the low frequency trends as well, because we're missing both ends of the spectrum, the low and the high. How do we get more of it? Shoot better seismic and have a wider bandwidth in your seismic. I mean, we've done that to some extent with broadband seismic, introducing more low frequency, but it's very difficult to introduce high frequency because the Earth is a natural low pass filter. So the reason why we lose high frequencies is because the Earth is layered, and layering is a low pass filter. So that's why we lose them. So it's very difficult to add back in higher frequencies. It's more amenable to get a little bit more in the low, which has been successful with broadband, but we can't go down to zero, unfortunately. It's not physically possible.
Okay, another question. Could you give a practical example of how we decide whether to go for high resolution with high uncertainty or low resolution with low uncertainty inversion? Are there any specific criteria or types of data that guide this choice?
I think in practice these days, we simply treat the trace, the relative impedance, as being the integration of the seismic trace, in which case it naturally generates the effective resolution. If you go to a deterministic inversion, then if it's model-based, then the way you constrain it is you just don't put too much high frequency in the model. If you're doing a sparse spike style inversion, then you have to put it in as an explicit constraint. And in fact, I'll show an example later on of where somebody made something, basically they put in too much of the high frequency, and it turns out with sparse spike, what you end up with is just the trace integration again, which I'll demonstrate later.
Okay. Nahla asks, could you explain how the dipole annihilator approach helps to resolve the non-uniqueness problem in seismic inversion and under what conditions?
Yeah, it doesn't in conventional seismic inversion, but it does play a role in theory when we talk about stochastic inversion. The problem with stochastic inversion is that we trade we say we get high resolution. I mean, we get fine layering, but of course it's completely non-unique, and it therefore has a large uncertainty associated with it. So it's always a trade-off between the two. But we're kind of digressing slightly between deterministic and stochastic inversion at that point, which is a topic I will come back to and talk about a little bit later on.
Okay, last question. In terms of subsurface accuracy, which method provides more reliable geological information, spiking deconvolution or recursive inversion?
I would just go for trace integration. So colored inversion is the simplest one, is the most reliable. Either trace integration, or if you have some well data available, then you would do it via colored inversion. Anything beyond that, you have to be very careful, mainly because of the low frequency model that's introduced. On the high frequency end, there's not a lot to choose between them. As long as they're properly implemented, then they'll all deliver good results. The real issue comes on the low frequency end, which I'm going to talk about later.
Okay, in the second point of average operator, in that part, do spikes pair like cancel out each other?
Well, in the dipole annihilator, they do. So if you do it in model-based inversion, you'll end up with a model that's got very fine layers in it, which are not real. If you do it through sparse spike inversion, it's actually self-limiting because you end up effectively with a spike for every sample on the input seismic trace, which effectively gives you colored inversion again. So colored inversion is the sort of the sophisticated end of trace integration. So in that case, Sparse spike is kind of self-limiting, but it is possible to end up with too many fine layers in there which are not real, and convince yourself they're real when they're not.
Okay, great. Now there is no more questions.
Okay.
We can take our break now because it's
Okay.
50 minutes.
That's
Okay.
very good.
Okay, the break will be for 5 minutes, and we will come back in 5 minutes.
Okay, perfect.
Okay, thank you so much.
Just a quick thing, actually. So quickly.
Okay, so I'm now going to talk a little bit about pre-stack inversion. So this is where we use information from not a full stack seismic, but pre-stack seismic. So this is AVO type information in order to get a little bit extra from the seismic. So, I mean, in theory, we could use what we would call sort of full AVO inversion of a seismic gather to estimate velocity, P-wave velocity, shear wave velocity, and density. And this would require us to basically use a set of equations called the Knott-Zerpritz equations, which sort of govern how seismic waves propagate. It's actually quite difficult to use the full implementation. So most commonly, some linearizations are used. They're actually pretty effective anyway, actually, the linearizations. The most well-known one is called Aki-Richards, which was produced in 1980. And it's a very long thing here, but you can see basically it's got angle terms in it, the angle of incidence of the wave coming in for our gathers, VP over VP, we've got VS rate, VS VP ratios, and there's a density term and so on here. So it's defined in terms of 1, 2, 3 terms, which are all defined in terms of changes in P-wave velocity, shear wave velocity, and density. So it's what we call a 3-term equation. Now, very commonly associated with this is Shuey's approximation, which is a very simple AVO equation, which is called intercept and gradient. The original paper actually is just a rearrangement of Aki-Richards, and instead of using VS and density, they use Poisson ratio. What they do is they create this equation here, and everyone thinks that Shuey's equation is this one, simple one written down here, which it kind of is, but this is the 2-term version. In this version, this last term has been truncated and removed, and we're only using these 2 parts, which is basically the term in the brackets here is the gradient, and this bit here is the P-wave reflectivity, the near offset reflectivity. What's worth noticing is that, in fact, Shuey's original equation is identical to Aki-Richards, but just rearranged. Mathematically, it's the same. So Shuey's got very unattractive terms wrapped up in that single letter, all kinds of horrible things going on inside this thing, which are horrible. I've never really particularly liked it, but it works very well in terms of intercept and gradient, which are quite familiar for anybody using AVO. So 2-term approximations tend to be thought of as intercept gradient. So we get from those potentially a P wave and a shear wave something, normally a P wave and a shear wave impedance. And with that, we can generalize something called extended elastic impedance, EEI, as a generalization of this. In a 3-term approximation, generally we're trying to recover the density as well, but it turns out this is very, very, very difficult to do because it is such a tiny contribution to the AVO equations. It only manifests at all at very, very high angles where we have problems with preserving amplitudes correctly, and normal move out, velocity modeling, and so on are also very difficult. So density is very, very difficult to recover. The most popular form of the AVO equations used for inversion is Fatty's equation. This is a 3-term equation here. So it's a reflectivity equation with a reflectivity for P wave, shear wave, and density here. Various terms appear in here, and you're going to see all these sine square thetas on. They'll appear later on when I talk about EEI as well. This is the Fatty 3-term. It's very widely used. But in fact, there's even a simplification of this. The 2-term of this, which basically becomes impedances, is actually even simpler. Now, what's worth saying here, people talk about Fatty, they talk about Shuey, and they talk about Aki-Richards. They are all 3-term equations, and they're all mathematically identical. There is no difference between them. So if you calculate the AVO curve from them, they'll give you the same answer. Shuey is a truncated version of Shuey's equation, which isn't very accurate. At about 20 degrees, it breaks down, and it definitely fails at 30. Fatty 2-term approximation is actually much better. and it's actually pretty accurate out to 30. And in fact, it carries on pretty well out to 40 degrees. So it's very commonly used as a sort of the go-to equation these days. This just highlights it here. Aki-Richards, Fatty, and so on. Shuey 3-term is all overlaid in magenta here. This is Shuey's 2-term equation here. This is angle along here. Shuey's 2-term equation is pretty poor once you go past about 20 degrees. Even at 30, it's starting to get quite in error. Fatty is actually pretty good out. 2-term is actually pretty good out to 40. It's actually quite a good approximation. That's just the reverse model, the other side of the interface. This is just a repeat again, just demonstrating the same point using a well-known online calculator for these things. What I'd like to draw your attention to, though, here is the full Aki-Richards and the full Fatty, which follows that as well, are actually, people talk about how wonderful Zerpritz is, but in fact, you can see here the difference in full Aki-Richards, 3-term Fatty or whatever, and full Zerpritz is negligible. For any practical use in seismic inversion, the difference is very, very small. There are far more errors coming from elsewhere in inversion than worrying about whether you're using full Zerpritz or not. So if you're doing large angle inversions, any 3-term equation works pretty well. That's the reverse model again. Yeah, this is just kind of parameter sensitivities. The density sensitivity is tiny. You can see even at 40 degrees, it's a tiny contribution. And it could be either polarity as well, which makes it very difficult to detect in seismic inversion. Yeah, and then just a final comment on these pre-stack properties. We can easily get 2 properties from pre-stack inversion in seismic, but we can't really get 3 because that involves density. So the 2 properties we get simply are either P-wave impedance or shear wave impedance. But if we get P-wave impedance or shear wave impedance, we can derive lots of other properties from these as well. So there are other inversion methods to things like VS over VP ratio. It's obviously just IP over IS or vice versa. And we can get other properties like lambda rho and mu rho, but they are simply rearrangements of the same equations. They're just squared terms or whatever. So any of these things like lambda rho, mu rho, VS over VP ratio and so on, all of these are just transforms of P-wave impedance and shear wave impedance. So if you've got one pair, you can derive any of the others very, very simply. You may prefer one particular pair depending on what the target problem might be, depending whether you're fluid sensitive or something like that, which again, I'll talk about a little bit later. We're going to see these generalized later on though in EEI. So that's all I've got to say there. Oh yeah, and there's the VP-VS ratio and the Poisson ratio. Again, IP over IS is VP over VS squared, it's the same thing because the density terms cancel out and the impedances. And this is Poisson ratio in terms of the same things as well. I don't particularly like Poisson ratio, but VP over VS is very useful sometimes for certain things that we're looking for in the subsurface and can be quite a good fluid detector or not. Okay, so that's really just a summarized pre-stack inversion. So pre-stack inversion, we get 2 properties from the seismic, not 1. So in single stack inversion, we get 1 property. Pre-stack inversion, we can potentially get 2 properties reasonably reliably, but we can't really get 3 because the density term is just too small and it just falls into the noise. Okay, that was a quick summary of that part. Any questions that come out of that a little bit?
No, there is no questions. We can move on.
Okay. So that then leads me to really taking the same ideas of pre-stack inversion theory and now talking about what we call extended elastic inversion. So this is just a generalization of those ideas. So when you talk about Aki-Richards or not Zerpritz equations or whatever, they're very specific to P-wave, shear wave, and density terms. Elastic impedance kind of is, but it creates an interesting generalization of angles that allow us to create single stacks from seismic data, pre-stack data, that we can actually just look at, which are optimized to try and identify particular properties that we're interested in. And one of the most obvious ones would be something like fluid effects, because obviously those may well be related to the presence of hydrocarbons. So elastic impedance is based on the same ideas of these equations, P wave, shear wave, and density. And you see here, I mentioned earlier, theta is the angle of incidence, and you've got sine squared in here. These are the general terms that govern seismic propagation. They're always the same, these equations. And then you've got K in here, which is Vs over Vp squared. So all of these equations are just like Aki-Richards or Fatty equations and so on. The clever part with this, though, and this was introduced in 1999, this came out of BP, was that Pat Connolly recognized that we could treat this equation here, the actual impedance as a function of angle. We could actually take out the P wave velocity here and enclose the rest of it as like a bracket term here. And what this term in the bracket effectively becomes is sort of an elastic density term. So it's rather like acoustic impedance from a sonic log is the sonic log times by density, bulk density. But if you introduce the angle term in here, the term in the brackets becomes a density as a function of angle in the seismic. And it turns out it's a combination of P wave, shear wave, and real density. If the angle of incidence is 0, this term cancels, this term cancels, and we just get back to bulk density again. So at 0 angle, this is just our normal acoustic impedance, sonic log times density log. But at any other angle, this term actually includes P wave and shear wave as well. This is what's called the two-term approximation, which includes sine squared terms in those. If you want three-term approximation, you put a tan squared at the beginning as well, which is more like Fatty's three-term equation. Now, why is this a useful term? Well, I'll show you why it actually turns out to be a very useful way to address using seismic data. One of the issues with it, though, before we move on from that, is that this elastic impedance, this term in the brackets here, scales with angle, which doesn't matter for calculating things like synthetic responses, but it's kind of inconvenient when you're looking at pseudo logs that you could generate from this in well logs to see whether or not a particular angle is sensitive to something that you're interested, like maybe shale content in the subsurface or something like that. So because it scales at angle, BP published a method of basically normalizing it in 2002, which is Dave Whitcomb. So the normalization is shown here, and he's just rewritten the equation. So the power terms here are the bracket terms here. What he did was he normalized it by dividing through by the average properties. And then you rescale it with the average impedance. By normalizing it, you get rid of this rescaling problem. Otherwise, it's the same equation. So this is normalized elastic impedance. So it's just a rescaling. So this is just how the maths works. The practicality of this doesn't really matter. But what Whitcomb then went on to explain in another paper in the same issue, it was a very popular issue of geophysics, was how you can treat the extended elastic impedance. You can describe basic rock properties as basically transforms using this equation. And one of the weird ones that he sort of showed was that if you project an AVO response to a negative angle of minus 1.25 degrees for standard properties, it would be equivalent to shear property. Now, you can't record a negative angle in seismic. It doesn't mean anything. But you can create a transform of your recorded seismic data to synthesize what you would see at that theoretical angle mathematically using these equations. So what you do is you take the linear form of these equations, just two term, so the effect of amplitude with angle, and you can then project what the response would look like. And you find then it turns out to be directly sensitive to rock properties and petrophysical properties that we might be interested in. So you recall, I keep pointing out that we got this angle term. The angle is what's actually recorded in seismic, like 0 degrees, 10 degrees, far offset stacks in seismic might be 30 degrees. But the linearity term of amplitude in seismic actually is the sine squared of the angle. So the sine squared of an angle of 30 degrees is in fact 0.25. So this is looking at a single reflection across a gather in seismic. And we're seeing the amplitudes across that gather. In our classic AVO intercept gradient calculation, Shuey's approximation, we fit a regression line through the amplitudes as a function of angle at a given time slice, time position for that particular angle gather. and we get an equation. Now, the intercept is Shuey's classic intercept, which is the near stat response, which is acoustic impedance. The gradient is, of course, another AVO attribute. What Whitcomb's saying is that we can actually project this line to any angle we like and calculate what the theoretical response would be. Now, why would you do this? Well, supposing you've got an angle like this, you can make whatever this is responding to here go to no amplitude at all if you project to this angle. Or if you project it back here, it might correspond to something that you're interested in. In order to do this mathematically, you've got sine squared theta is what the seismic actually calculations are based on, but mathematically that only exists between 0 and 1. So in order to turn this into something which is calculatable over any angle, you get rid of sine squared theta and you replace it with another angle called chi. So tan chi equals sine squared theta. It's just a substitution. And this then allows you to actually treat the equation as having infinite bounds. Now, why would you do? I mean, this is just the equation here. We just changed the sine squared theta terms for cosine chi terms and sine chi terms. It's otherwise the same equation, but now mathematically manageable. Why do we do this? Well, it turns out that certain angles correspond to certain properties of rock physics. So, for example, the VP over VS ratio is proportional to a chi angle of 45 degrees. Shear impedance is minus 45. Lambda and K and so on. I mean, we kind of knew this, but this kind of creates a framework that it's very simple to use and very practical. Now, how practical is it? Well, the EI0 volume is the intercept, acoustic impedance. A gradient impedance would be EI90, so that's like the traditional gradient volume. So we can calculate any volume in between using gradient and intercept, just like we would with Shuey's equation. Why is it useful? Well, because we can do clever things with it. So let's have a look here. We can cross-plot our well data in terms of acoustic impedance and gradient impedance. So this is EI chi angle 0, which is acoustic impedance, and 90, which is equivalent to the gradient in AVO terms. So we can plot this with our logs, and here it's color-coded by shale volume. So what you can then see is that there's a very clear separation between sand and shale, and it's along this direction. What is that direction? This is 0 degrees, this is 90. So we can rotate our rock physics to some specific EI angle, where now this direction gives you the maximum separation between sands and shales. Now, if we can do this for our petrophysical data using our well logs, we can do this for seismic. So the idea with EEI is to generalize AVO and come up with a rotation angle that we can derive the response of the seismic for that angle, which is calibrated, if you like, to be most sensitive to something that we're interested in. Here, it's most sensitive to separating shale from sands. So in this case, if we were looking from the left, shales would appear soft and sands would appear hard. The sands down here, we look at those in detail. Now what we're doing is we're showing those color-coded by water saturation. So on this rotated angle now, what you see is that low water saturation, so hydrocarbon saturated sands, sit out to the left. This is the classic fluid effect that we sometimes can see in seismic. It's more pronounced if we have gas than if we have oil, but we might see this as well. So now we've got two properties. On this axis, we're separating shales at the top from sands. On this axis, we might see the contrast between hydrocarbons and not hydrocarbons. Why is that important? Well, what we've done by this rotation is we've effectively, if we look on this property, we've effectively made sands and shales look the same, and we've tried to maximize the standoff, if you like, or the amplitude that we'd see in seismic for a fluid effect. So we're optimizing our seismic by these projections. So this would be oil sands in this case. Another example here, we've gone through and we've looked at P impedance, shear impedance here. This direction would be some kind of impedance fluid indicator. So this is our our shale line. These are our sands here. These are oil sands and gas sands. So this direction is a fluid indicator. If we just take P impedance, zero offset seismic, what we see, if we look at the impedance fluid direction, here, you can see that that fluid direction, if we separate our data into that, we can see very clearly oil and gas over here, and we can see water down here in this particular projection. So we can try and separate fluid effects. Another example here, not a fluid effect, but trying to distinguish sands from shales. When we look at conventional seismic angles, we can't see any separation. And we see that there's no correlation between acoustic impedance and the gamma ray log. But if we compute this EEI for different angles, we can generate a curve looking at the correlation of the impedance log in the wells with the gamma ray log as a function of this angle, and find the angle which best describes shale properties. So you see that here. So if I look at histograms of sands and shales for acoustic impedance, velocity times sonic velocity times density, there's no separation. They look the same. But if you compare them, you see that they don't have any real relation to each other. This is lots of wells concatenated together here. But if you choose different EEI angles, so you calculate this in your well logs, you find that at some angle here, the correlation gets better. So if you look at conventional seismic, it sits in this range. There's no correlation between sands and shales on conventional seismic. If you look at this projection over here, we find that at this angle, we start to see a correlation between the log, the EI log, and the gamma ray log. And if you then generate a histogram at that angle, what you find based on sands and shales is that now they're separated. So if we generate this in seismic, we'd expect to see sands as soft and shales as hard. So we're generalizing the AVO equations here to try and identify properties that might be useful to us. And then we're trying to convert the seismic to look like those properties. And of course, if we can do that and optimize it, then we've got a very simple route by which we can then invert to get the actual properties from these individual orientations that we've generated from the seismic. And that's then what the gamma ray log, it tracks now. The gamma ray and the EI log at that angle track quite well. Yeah, I won't cover that one here now. Oh yeah, I will actually. This is quite useful. This is just showing an example of a synthetic seismogram, showing that as you rotate the EEI from -90 to +90, you actually go through a phase reversal here, where the amplitude goes to a minimum. And in fact, around this angle, which is close to far offset stacks in seismic, is where you become most fluid sensitive. So you can actually, without well control, you can actually find this angle in seismic, because you can generate these projections from the seismic pre-stat data and then look at the energy you see in a window over the target. So what you'd see is it's very bright over here because you get very strong reflectivity. What we've actually done over here, we're kind of looking at shear properties, and we've removed fluid effects. And it goes to a minimum somewhere here. That minimum is where the phase reversal occurs. And if we just go about 2/3 between 0 and that angle that we see on our seismic to about here, generally speaking, we would see most effectively our fluid properties. So we might see hydrocarbon discrimination. So we can actually do this without well control as well. Sometimes this is called the lithology cube, and sometimes this is called a fluid cube, although it's more of a pore space cube than a true fluid cube. Okay, that covers our pre-stack methods.
Okay, we have 3 questions.
Okay.
The first question, in practice, do we usually see improvements in fluid discrimination when using 3-term inversion compared to 2-term approaches?
No, generally fluid separation, you only need to use 2 terms. 3-term approximations to fit the seismic are okay, but we still only get 2 attributes back reliably, a P wave something and a shear wave something. And the shear wave with the P wave actually gives us the most information we can get about fluid discrimination. So we might get P wave, shear wave. We might use EEI, in which case we get lithology fluid, but they're all similar types of styles of using the data, just trying to optimize in a different way to get the most out of seismic. But there's always a way to try and get out the best fluid effect. But normally going to 3-term won't make that much difference to it. It's not really that relevant.
Okay. Someone asked about in slide 8, How does projecting AVO in sine squared theta helps us distinguish between fluid effects and lithology effects in seismic data?
Okay, so we're calculating what the amplitude would be for our reflection at any angle, for example, out here, negative or positive. That is effectively, so if we take 0 here, 0 angle is acoustic impedance, plus 90 degrees in chi would be gradient impedance. So these are our limiting cases here, 0 and gradient impedance. And so what we're doing by projecting along an angle is we're effectively taking this cross plot and we're rotating it. That's what those projections are. So here you can see that we now make, on this direction, looking this way, we make sands and shales look the same. But when we zoom in at the bottom, we get the biggest separation of fluid effects. So that's why we do it.
Okay, in the same slide, what is the practical impact of the range of linear observations being smaller than the physically realizable range?
Yeah, I mean, that's an interesting point. So obviously, as you project over here, thinking of the straight line, you will get increasing an error envelope around that line as you go out. So what tends to happen is you can sometimes lose a bit of high frequency. You tend to get it more dominated by low frequency when you do this. So you've got to be a little bit careful, but in practice, it works reasonably well.
Great. Last question. Why do we use S impedance instead of Poisson ratio?
Some people do use Poisson ratio. I think that P wave impedance and shear wave impedance, or sometimes the ratio of the two. So we use P impedance and then we use VP over VS, or vice versa, depending which you prefer. It's more convenient. Poisson ratio is used in classical AVO, but it's not as easy to kind of mentally, I think, think about what it means. Whereas a shear impedance removes fluid effects very effectively. So I tend to think of shear impedance in a more simple sense. But you can use any of these. They're all calculable from the two properties we get back from pre-stack inversion. You can calculate any of the others. So you can choose whichever one you think is most appropriate in your particular rock physics case that you're dealing with.
Okay, there is one more question. If the elastic impedance relies on linear zero Bright's equations, how accurate can it be in a reservoir with strong anisotropy or fluids effect?
It's very good at fluid effects. Anisotropy should have been handled again in the imaging. We assume when we get to inversion processes and AVO processes that the data is properly imaged and any effects like that have been corrected for. One point to make about EEI is that you are really restricted to using the sort of 0 to 30 degree recorded angle range in seismic, because that's the range over which the amplitudes are approximately linear. So you are restricted. You're not really going to use very far angle stacks in that process.
Okay, great. We're done with the questions. We can move on.
Okay. Right, so we've got a little bit on inversion algorithms. Let me just check how many slides are in here. I want to see. Okay, again, it's quite short. Okay, some inversion algorithms. So there's lots of ways we can group inversion. We could do post-stack inversion for things like acoustic impedance, or a single EI volume if we wanted to. So that would be the second case. And then we could do pre-stack simultaneous inversion, where we might try and get IP or IS combined or something like that. Integration, of course, is the fundamental principle in all of these. We can group all these methods that you might see from different contractors. You might get constrained sparse spike, GLI-based simulated annealing, Monte Carlo methods. These are all really just mathematical tools to solve the inversion problem. They have varying trade-offs for smoothness and performance and so on. The specific choice, providing it's properly implemented, doesn't really make much difference to the result. So any of these methods will work if they're run properly. There are slight advantages and disadvantages to some of them, but to most practical purposes, it's not that important. These are all what we call deterministic methods, actually, when we talk about this. And I want to talk about something here about amplitude spectra. So integration is based, the principle of integration is based on, first of all, knowing the phase of the seismic. That's normally very well handled in seismic processing, and particularly if we have well control these days. The seismic spectrum if you're going to integrate, must be blue. It must look like this. So from low to high frequency, it must decay. The so-called blue spectrum, sorry, must be like this on the right, blue spectrum on the right. It must increase. So red spectra is a decaying spectrum like this. This is actually the spectrum of impedance. This is the spectrum of reflectivity. Now, when you invert, this doesn't matter too much because you know that you're trying to say you know the wavelet, so you have to extract the wavelet first. But if you're just going to integrate the seismic, it needs to be blue before you integrate it. And when you integrate it, you end up with red on the left, which is impedance. Now, interestingly, modern broadband seismic data is actually often supplied with a spectrum that is red because they tend to keep the low frequencies very enhanced. Modern methods, they tend to be close to zero phase anyway. So broadband seismic actually has a zero phase spectrum, but the spectrum is actually red. So what it actually is, what you're being delivered is actually impedance data, relative impedance data, but with a phase shift of 90 degrees, which is the difference in impedance and reflectivity, which is probably the worst of both worlds for picking data. So just be aware of this. So this is a classic bit of processed broadband seismic. And interpreters hate this because it looks horrible when they're trying to pick it. If you did spectral bluing on this, you'd end up with something like this, which is now lovely for picking. So this is now proper reflectivity data. You blued it and you've changed the balance of low to high frequency. You haven't gained or lost anything. You've just changed the balance. It's now reflectivity data proper now. And this is what you really want for picking on. So if we think about geophysical assumptions that control our seismic inversion processes, well, we can think about zero phasing and amplitude spectrum shaping, and then kind of wavelet removal by assuming a blocky layered earth. These give us relative impedance methods, one of which is colored inversion. If you then add a low frequency model, we're trying to go from a relative impedance to an absolute impedance. So an absolute impedance is impedance measured on a scale from 0 to something. Relative impedance is fluctuating around 0. So if you try and add a low frequency model, you get what we call absolute impedance. And then we can go a stage further and we can add in this non-uniqueness, dipoles, if you like, thin bed effects. In this, we're perturbing the low and the high frequencies outside the wavelet bandwidth. Now, in the wavelet bandwidth, the seismic bandwidth, the inversion is effectively unique, largely unique. It's thick bed layer averages. Outside the seismic bandwidth, it's no longer constrained by the seismic, only by any well data you introduce and any spatial constraints you put on. And that's when we enter something called a stochastic impedance. The problem with stochastic impedance is derived from geostatistics. At that point, you're in a model which you have to deal with lots of realizations. There's no single model that you can generate. Absolute impedance is what we call deterministic inversion, and that generates a single model, like a Kriging, if you like. Relative impedance has no low frequency in it generally, and it's just alternating between positive, negative polarity data, more like normal seismic. So relative impedance is the simplest form of inversion. We can achieve it simply by integrating the trace. It's reversible if you define it with a smooth filter like a dB per octave filter. If the original seismic is useful reflectivity information, then relative impedance works. So relative impedance always works. It's a seismic attribute. It's brilliant. The information content, the resolution are pretty much the same as the relative reflectivity you started with. So I call this relative impedance, or RI here. In an absolute impedance, we're formally trying to invert, trying to estimate the true impedance of the layer. So we need two further assumptions. We need to calibrate the variability to somehow match the well data, and we need to add in the low frequency. And we normally call this a deterministic inversion. So the variation of relative impedance has to be calibrated or scaled. Now, scaling doesn't change the information content, and then the missing mean value is added. So that has to be some kind of low frequency component. Simply, it would just be an added DC shift. But we can't derive this from the seismic trace. So it has to come from somewhere else. Typically, it comes from a model and well logs interpolated. So a deterministic inversion is a relative impedance inversion to which we've added a low frequency model. And this is a very important distinction. So seismic relative impedance is this part that we actually measure in the seismic. A deterministic inversion fills in this part, normally with interpolated well data, or sometimes with interpolated seismic velocity data. A stochastic inversion is also an absolute impedance method, but we treat both the missing low and high frequency information, and we don't add it in as a smooth interpolation, but we add it in as something that varies in a way that we control, typically with a variogram. So this is much more like geostatistical simulation. It's like a Monte Carlo style method. So in this now we simulate well data in the low and the high frequency. But of course, this means that we generate multiple realizations. So this is a very specialist tool and is not often used. And when it is, it tends to be very specific to reservoir type conditioning problems. So we tend to talk about inversion in terms of wavelet removal. We kind of attempt that in any type of inversion, relative, deterministic, or stochastic. The time domain appearance of the wavelet with its side lobes and so on is actually really, it's a manifestation of the bandwidth limitation. Now, we tend to think that we can remove the wavelet, and this is desirable because it's assumed that this will remove the side lobes and therefore remove the tuning effects. But this isn't really what happens in most inversions. What happens in a determinist inversion is the Earth is considered to be a sparse, blocky layered model. And by making this assumption, we appear to remove the wavelet. We don't really remove the wavelet. What we're actually doing is replacing an assumption of continuous reflectivity with the assumption of layer average, a layered Earth with sparse reflectivity. So we're actually trading detail to get a locally smooth blocked average. That's not removing tuning when we do this. The bandwidth remains the same. The only method that actually removes tuning of the three I've talked about here is actually stochastic inversion because it's broadband. So determinist inversion doesn't really remove tuning, and nor does relative impedance. There are ways to get at tuning, which is very important, and I'm going to, hopefully if we have time, I'll get to those. But determinist inversion is not an effective way to remove tuning from seismic traces. Okay.
So now we don't have any question. So
okay, good. I'm going to miss out section 6. It has a little bit about sensitivity. So I'm going to go to the low frequency question because I think this is quite important. And then hopefully that will get me on to a bit of detuning then quite quickly. So I've already said that, let me just, sorry, just want to check how many slides I've got. Give me a sense of how quickly I need to go through this one. Right. I've talked about seismic being band limited. And the real issue for us is that it has no low frequencies. So it doesn't include absolute information. And we can't recover the low frequency model properly from the seismic. So that means that inversion cannot give us the true value of impedance. It only gives us local variations around some unknown value of the actual impedance, what we call relative impedance. So in a deterministic inversion, we model the Earth as sparse, blocky, layered. We think that we're doing that, we remove the wavelet, although we don't really. We kind of replace one assumption with another assumption. To make these absolute impedance estimates, we must add in the missing low frequency. And typically this is modeled using interpolation with wells. We may be guided by seismic picked horizons and faults. And maybe we use seismic velocity information as well. They all help a little bit. But if you remember, I showed you this earlier with Oldenburg's theoretical paper showing you that you can go around this loop. And if you start with that, you don't end up with that when you go through basic inversion. You lose the low frequency. So we have to add it back in again somehow. Now, a determinist inversion works quite well if the layer system is thick layered, but it doesn't give us true impedances. It can work with thinner intervals, but only if we've got very conformal layering. It doesn't work so well when it starts to get tuning in it. So this is an example of strong reflectivity here with some nice well-defined layers. You can see here, thick bedded layers. This is actually based on extended elastic impedance, but a single volume inversion. You can see here that the inversion does reasonably well at showing sort of certainly one layer through here and possibly a second layer here with, as it gets thicker, a little bit of separation over here. It doesn't seem to do too badly. And we can see in map form, it's not done too badly. It's sort of given us some amplitudes over here in the sands over here, which are quite bright. And you kind of look at it and think, well, you know, it's kind of seems to be working, and we've transformed it here, absolute impedance into porosity, and maybe it's working. It shows up these sands, perhaps. The real issue, though, is because we don't have low frequencies, we add in those low frequencies from somewhere else, and they're very simply interpolated very often. This leads to a danger when looking at deterministic inversion. And the danger is that if there's an artifact in the low frequency model, then you will see that as an artifact in the inversion result. And this can be a pitfall for seismic interpretation. This is a good classic example. This is actually from the Kadamwari field in Pakistan. This is a model-based inversion. You've got a well here and a well here. The sands are low impedances here. So we know we've got a bit of sand running through here and in this well here. And then there's another sand here that we know doesn't reach this well. So this was the inversion result, and everyone was very excited, saying, well, look, it must stop about here. Except the trouble with that interpretation is that when we look at the model, we see that that's the way the model's been interpolated. So that conclusion is not actually in the seismic, it's a conclusion that's coming from the model. Another example here, this is interpolation of a low frequency model. You can very clearly see that these could give rise to artifacts in the same way. And this is a horizon slice to a third model. This is the model. That's what we see in the inversion. And these are clearly bullseyes around the wells. They're not real, they're coming from the low frequency model. There's not enough seismic information to overwhelm it. This is a very specific example. This is a model. This is an example. I didn't do this one, but this is an example I saw many years ago that I've used ever since. So this is a sparse spike inversion, deterministic inversion. It's actually Algeria. Actually, this is not onshore Algeria. And reservoir sits, I think, somewhere down in here. I forget exactly where, somewhere in here. It doesn't really matter. This is the final sparse spike inversion. It looks okay. We see quite good layering. We see some detail. I was asked to review this, and I kind of reviewed this by pulling out the low frequency model. How do you do that? Well, you can filter the seismic result, the inversion result, with a low pass filter, and you'll see the model. And this is what you see here. And as soon as you see this, you see that there must be a well here, there must be a well here, and there must be a well here. How do I know that? Well, because I can see the bullseyes in the low frequency model that surround them. And you see it down here. This is the reservoir level down here. If you high pass filter that full inversion result, this result here, and high pass filter, you see what's coming from the seismic. And this is the element that's coming from the seismic. And at that point, it doesn't look anything like as exciting as it did when we introduced that well model. The problem I've got here is that this is what the bandpass part of the full inversion that was very expensive shows. But if we just taken the seismic trace and integrated it, it would look exactly the same. So I just want to demonstrate here to you, there is a slight difference. That's because they didn't like the noise, so they did a 3-trace mix. But essentially, the sparse spike part coming from the seismic looks exactly like a trace integration. There's no difference. So the full inversion is simply an interpolation of the wells added to the relative impedance. So the seismic element comes from this relative impedance part. Inversion also, it's an averaging process. So we tend to see smaller variation than we do in the wells because we're only recovering local averages. And so you see that in this case here, this is a layer-based inversion. And you see that the inversion gives you this kind of variability because it's a layer average in the sand. So this sand runs through here. It's actually a hard sand. This is onshore USA. It's actually a hard sand here. We see it. It stands off. We can image it quite well. But when you overlay the well logs on either side of it, you see they have a lot more variability in them than we see in the seismic. And that's because the seismic is inverting to a much simpler average than we see in the sort of thinner bed that we would actually see in the well data. Yeah, we can modify the model outside the wavelet bandwidth and it won't affect the convergence of the model with a seismic trace. So we can apply scalars or shifts and it'll look the same. So just to prove that, you change the low frequency model and then you look at the fit to the seismic. The two inversions here look the same, but actually the model on the left, the model that was used for this one, was scaled half the model on the right. You wouldn't tell the difference within a scaling factor. So if the model's wrong, the absolute impedance is as wrong as the model is wrong. So be aware of this as well. The seismic inversion can't tell the difference. The model is just passed through. If you've got a good model, fine, use it. But just be aware that there are these limitations. How do we better introduce trends into our inversions? The best way is through some kind of interpolation. But normally it's better to try and estimate vertical trends independently and use those, because vertical trends are based on very important physical assumptions like compaction trends. So it's often better to divide up the model into layering, use compaction trends as a first step, and then only interpolate laterally as a second step. So if you've got trends running through the data, that they can be very useful and they could be important. Again, though, be aware if you're going from something proximal, where you have well control, to something distal where you don't, then the trend may not still apply. So just be a little bit careful over that. But vertical trends are much more effective if you build them into your models for deterministic inversion. Porosity loss in sands is probably close to linear than it is with depth in shales. Chalk in the North Sea is pretty close to a linear trend. That can work very well. Porosity loss is not sufficient, though, to explain everything. So, you know, if you're going to do depth trends, though, generally, if you're looking for sands in mostly shale, then normally what you do is you build the background model by removing the sands from the calculations. You put in the background shale, and then you revert for the sands from a shale background model, and that can be more effective as well. Lots of seismic companies are very aware of this when they do seismic inversion these days, and these are often the methods that are used to build these models. V0K functions could be used in depth conversion. Linear functions, they're local depth fits, but really they should be in asymptotic slowness functions, really, because obviously you asymptotically approach a maximum velocity as you close porosity space and microfractures as well. You could constrain these models with seismic stacking velocities. That's sometimes done. It gives you some very low frequency, very real measurements, and certainly if you've got very good quality stacking velocities, then they can be useful as well to constrain the low frequency. However, they can be noisy and you may need to get artifacts out of them. Sometimes that can be bad, but modern processing is much better in this regard. And again, you can create well velocities with stacking velocities to get low frequency trends, is just shown in 2D map form here. Dix interval velocity can be used again to get these, and I think there's an example here. There's sort of old school velocities can be very noisy and very unreliable. Modern ones are much better than this. But they can, again, this has still got artifacts in this particular example, which have been induced from the size of velocity. So you've got to inspect this very carefully, and you've got to think very carefully what you use. But modern velocity fields from modern imaging are much better quality than perhaps the example I've shown here. So these are all ways in which you can get a better, more reliable, low frequency model in a deterministic inversion. So any questions at that point?
Yes. Malak asked, how do anisotropic assumptions affect the reliability of low frequency model in elastic inversion?
Well, again, I would go back to what I've said earlier, which is that you assume that the anisotropy has been taken care of properly in the seismic imaging, and that we're only inverting a properly formed image where those effects have already been accounted for in the seismic imaging.
Okay.
We don't account for them in the inversion.
Second question, if we have unconventional reservoir, for example, how challenging is it to build low frequency model for density?
Depends what kind of unconventional reservoir it might be. I mean, if it's onshore heavy oils, for example, then you can still build a model for it. But it depends what form the unconventional reservoir is. I mean, if it's fractured reservoirs, that kind of thing, or if it's reservoirs where you're looking at shale gas or something like that.
I think it's about shale gas, yes.
Yeah, if it's shale gas, then you're not really looking directly for seismic properties in the traditional sense for things like V-shale or something like that, or fluid effects. You're more likely to look for fracture, the ability to fracture the reservoir, so brittleness, things like that. That actually takes you back to the conventional seismic inversion for P wave, shear wave type properties, lambda, mu properties, that kind of thing. So you're back to sort of conventional rock properties. So there's no real change there. You can still invert for those things. I know that I've done inversion courses for Chesapeake in the US, and they've successfully used pre-stack inversion to get basically the fundamental rock properties K, mu, or lambda, and use those to sort of try and guide where they think the reservoir will be most susceptible to fracturing.
Okay, great. We're done with the questions.
Okay, so just looking here, let me just check what I've got. I'll just close a couple of these.
Okay, I just want to remind you, we only have 25 minutes limit.
Yeah, thank you very much. Very kind. I was just looking at that, and I'm just going to make decide what I'm going to show. So I've looked at pre-stack models there. I'm going to look now at detuning, which is slightly away from inversion, but I like this because it takes us more into QI work, and it also really, I think, emphasizes the practicality of using relative impedance as an ingredient. The section I won't have time for would be looking at very sophisticated things going into reservoir models, but this one is perhaps more generic and maybe more appropriate for some things. So when we think about amplitude variations in seismic, they're due to lots of geological factors, and we know that their interpretation is not unique. But something that I think we forget, particularly as geophysicists, is that the primary reason for amplitude change in seismic is actually thickness variation. So it's not the things that we're excitedly looking for, like fluid effects or shale effects or porosity. It's actually thickness change which drives an awful lot of seismic response. And a thickness change can give you an amplitude change of 100%. Now, of course, there are amplitude effects that we're very interested in. A good one would be the presence of hydrocarbons indicated by DHIs, direct hydrocarbon indicators. But if you think about a DHI response in a soft formation where we replace brine with gas, so think Nile Delta, I mean, is a good example. The maximum brightening you get is about 25% brightening due to gas. So thickness effects are much bigger potentially than even gas effects. So they're very large effects, and yet very often we don't take them properly into account. Lots of amplitude work these days is now routinely performed on relative impedance rather than reflectivity data. And it can lead us into estimates of things like seismic net pay, which is a reservoir quality measure, or porosity, and it may be leading us into looking for the presence or absence of hydrocarbons. The problem is that the impact of thickness change and tuning that goes with it on a seismic impedance volume means that the amplitude is primarily varying as a continuous function of thickness and not the geological properties that we're interested in. So if we want to interpret the amplitudes, we've got to think about the impact of thickness and correct for it if possible. And that should then leave us with a much better geological signal that might give us reservoir quality or fluid effects. Now, geophysicists are very familiar with the idea of time thickness and amplitude of a reflector, giving us a tuning curve with a peak amplitude that then decays to some constant. Now, that is true for reflectivity, but it's not quite true for relative impedance, as we're going to see in a moment. So this is a map, actually, I showed you this earlier from a deterministic version. This is actually the relative impedance from this data set. This is a horizon over the reservoir interval. So this is the extracted relative impedance for that data. And I'm showing you the amplitude map here. And you can see I've highlighted with polygons some bright events here in the north, some here in the middle here, a little low here. And I've also marked on the field outline down here. This is the original amplitude map. If we remove the effects of amplitude which are caused by thickness, so we remove tuning effects, the amplitude map looks like this. It changes dramatically. We now see that these bright features that I highlighted with polygons are in different places. The bright features in here have gone because they were tuning. The field outline is much better defined, and we get better amplitudes restored in this part. And we see this feature here is now turned out bright. So going from this to this is entirely changes in thickness. So these effects are very, very important. So if you're interpreting amplitude maps and you don't account for thickness, you may run into misleading results. So if we're going to detune seismic, we can take any relative impedance to do this. It could be color inversion, phase rotated reflectivity data, or even a deterministic inversion that we filter off that low frequency model. It could be full stack seismic, it could be a near stack or a fast stack, it could be an EEI volume, fluid or lithology volume, or it could even be the IP or the IS output from a pre-stack inversion that we've removed the low frequency model from. However, detuning is often used now in combination with a process called seismic net pay to estimate reservoir quality. And this is really derived from extended elastic impedance, EEI. And this is kind of the workflow that's very commonly used in exploration and in appraisal now for many, many fields. So the EEI workflow tries to separate the data into lithology and fluid effects. Most major companies use this now. There's lots of examples where this has been successful. And then we add detuning over the top and what we call seismic QI using seismic net pay. Originally for turbidite and fan systems, but it actually is very effective in lots and lots of sand, shale type problems. So why is the combination so powerful? The EEI creates a separation into two useful pre-stack properties, lithology and fluid typically. That is a significant help for interpretation. And then we can try and generate these pseudo net to gross maps using seismic net pay. And the detuning part takes care of the amplitude part where it's driven by thickness. I've done examples of this offshore Namibia recently, Equatorial Guinea. I've done it onshore Tunisia. And I'm going to show you a quick example here at Azanor in the North Sea, the Goose Prospect, the farming out. So this is detuning of an EEI fluid cube. So this is a fluid effect, but they couldn't farm this out. So this is their section from their farm out brochure. And this is this bright amplitude here. This is a discovery. This is the Claymore field. And you can see it's got lovely bright amplitudes and it looks great. And everyone goes, this has got a DHI on it and it's really strong. Their prospect was over here on the other side of the syncline, again, looking like a very, very obvious trap. But the concern was it doesn't look bright. It's not as bright as what they see on Claymore. So everyone's saying, well, there's no DHI, so it's going to be, there's no hydrocarbon effect. So they couldn't farm it out. So when you look at it, what they did was they took this in and they detuned it. So now on the left, you see it detuned, and on the right, you see it detuned. It's a slightly different line. So this is the Claymore field detuned. This is their prospect detuned. And what you see now is that the reason why it's not as bright is because it's thicker. Claymore is bright, and particularly bright. It's not just a fluid effect, it's also a partial tuning effect. Their actual reservoir is thicker. And so actually, when you detune the two, they now look the same. And so when you see it on a map now, their prospect sits here. The Claymore field sits here. When you detune them, they now have very similar amplitudes. And so this now perhaps points the way to saying that this is potentially drillable. And this is the basis of their farm out. So let's have a little look at tuning response curves when we're dealing with relative impedance rather than reflectivity. So in relative impedance, the tuning curve comes up, reaches a peak, and then it decays. And it decays continuously because we lack low frequency in the seismic. Obviously, it decays this way because we lack high frequency in the seismic. Somewhere down here, maybe 10 milliseconds, something like that. Typically, we might have our thin bed limit. We also see on real seismic very thin looking effects. They're actually edge effects of the wavelet, and they're not real usually. Now, one of the interesting things about the tuning response curve is it's independent of how strong the reflectivity is, how big the contrast is in impedance. They're actually independent of the amplitude of the reflection. That means you can actually detune anything without any other information other than what you can get from the seismic. You don't need a well to detune the seismic, very interestingly. They are bandwidth spectrum dependent and they're very sensitive to low frequencies. So changes just a few hertz will dramatically modify the curve. And they could vary spatially, but they obviously vary in time because obviously the frequency content of the seismic changes in time. So here are some theoretical models where we've chosen a fixed low end frequency, and we've changed the high frequency. And you can see the tuning curves don't change very much. But if we fix the the high end and change the low end, you see they change dramatically. So over here, 14 hertz would be like onshore seismic. That means that the maximum thickness you can see in relative impedance is probably less than 40 milliseconds. Offshore marine seismic, standard seismic might be about 8 hertz, so you might see 50 milliseconds. Broadband seismic, you might get to 70 or 80 milliseconds, something like that. So this is effect from going from onshore seismic to offshore marine broadband seismic. So broadband seismic is a really good thing for seismic inversion. What actually happens? Why is it insensitive to the strength of the reflection? Well, here is a weak reflection, stronger, stronger, stronger. The tuning curve just scales with the strength of the reflectivity or the impedance. So these curves are all just scaled effects, scaled curves of each other. What do they mean? They mean that if you were looking at a constant rock property as a function of time thickness, they would follow a curve like this on amplitude. So what we're seeing here is on relative impedance, the amplitude varies continuously as a function of thickness, even though the rock properties are not changing. If we correct for thickness, then these curves would now be independent of time thickness. So they'd show constant properties. So now you can see that this not bright amplitude here and this amplitude here are different rock properties because they're on different contours. Now imagine that you're looking at a at a sand down dip. Let's say it's down dip and it's thick and it's thinning onto a structural high. So here it's 35 milliseconds thick and it's got this amplitude here. Let's say it's a brine sand and that brine sand is thinning up dip onto a structural high. Here we go, we're going up dip, but its rock properties and its fluid are not changing. But it would still brighten as you go up dip because the thickness is changing from thick here to thinner. So the change here would actually cause the brightening. And if the thinning is conformal to structure, the brightening would also be conformal to structure. So this could give you a false DHI. Now, Connolly published a very effective method for estimating seismic net pay from amplitudes, where you extract thicknesses and average amplitude from relative impedance, detune it, and then you calculate what's called a seismic net to gross. And it's very effective. You can basically get a reservoir quality indicator very effectively. Now, the reservoir quality part needs well control to calibrate it, but the tuning part does not. In fact, you can use this for any cumulative petrophysical property. It could be B shale, it could be porosity as well. How does it work? What he says, if I got a sand here, a sand here, and a sand here, these three different sands, what he says is that the amplitude I see, if the amplitude followed the 100% sand curve, it would look like this. If the amplitude is not 100%, then at a given thickness, the ratio of that amplitude to the 100% sand line is a measure of the net to gross. So in this sand here, if that amplitude was what we saw, the ratio of that to that is 41% net to gross. The same amplitude at this thickness is 48% net to gross. The same amplitude at this thickness is 91% net to gross. So you can see that what he showed was that the same amplitude means different things at different thicknesses. So you've got to remove the effect of that tuning if you want to understand what the reservoir properties are doing from the amplitudes. Very important. Typical workflow, you do EI, seismic conditioning, do your projection, you do colored inversion, and then you detune it, and then you go into QI. So I'll show you a quick example here. This is the sea lion field in the South Falkland Basin, the north part of the South Falklands. This is the acoustic impedance. This is the elastic impedance here. And you can very clearly see here, it's class 1 AVO. The sands are hard and the shales are soft. So if you look at it this way, lithology projection, the shales will be soft here, the sand's hard looking in this direction. That would give you very, very good separation of shales from sands. It's a lithology projection. If we calculate that projection and look at impedances on the well logs, you see the shales are here, non-reservoir, sands are over here. And at that angle, there's no discrimination between pay and reservoir. So there's very little fluid effect because the sands are quite hard. At the fluid angle that goes with it, again, there's very little separation between the fluids. You don't see a fluid effect here. So the best we can do is reservoir quality. So how do we get that? Well, This is a time thickness map from one of their fans. So you can see it's thicker here, and at the distal end of the fan, we've got these nice, well-behaved fan behavior that we can see. We look at the amplitude map for the same fan. You can see this lovely brightening in the distal end of the fan. So we've got lovely brightening here. And of course, the eye goes to this and we go, oh, what's this brightening? Must be something important. But of course, if it's thinning, it may well be that this is tuning. So if we actually perform seismic net pay on this, we're detuning it and then we're calibrating it, the amplitudes, to a net to gross calculation, and then we multiply by the thickness, we get what we call seismic net pay, which is a measure of net sand thickness. So tuning curve fitted to the actual data here, the seismic time thickness and the impedance. And then we can take our EEI attribute. So this is our colored inversion, this is our amplitude map, and we convert it to detuned amplitudes. And now you see this brightness here is no different to what we see elsewhere. And then we multiply it by the calibrated to the wells and multiply it by the sand thickness. We get sweet spots. So these are where we have the best net sand thickness and quality here and here, actually in the feeder system. And it's probably okay quality, but thinner in the distal end of the fan. So Connolly is great, but it's only applied to maps. So I'm going to show you a method now where, for the same kind of system and the same data set, I'm going to apply this directly to the seismic. So it's a novel method to kind of do this on the seismic. So this is a seismic model here showing you with constant rock properties how the relative impedance amplitude varies with thickness because of the thickness effect. So if we apply this procedure to the seismic, we would reveal that there should be no variation through here because the rock properties are constant. So we can detune the seismic itself potentially. When it gets very thin, we can't do it. Here's our brightening peak tuning here, and we can remove that effect. So this is an automated process that doesn't need any picking. So if you apply this to the seismic, here's an up dip well. This is another fan in the same area in the Falkland Basin. Up dip, it's very clean, very thick, relatively low amplitude, actually average here. Down dip, this is brightening considerably, but the reservoir here is thinner and is shalier. So it's about close to 100% net to gross here. It's about 70% net to gross here. But it's actually brighter here than it is here, but the rock physics says it should do the opposite. So what is actually causing that? It's the tuning. If we detune the seismic response, you can see this thin effect down here. The amplitudes have been much more muted. That brightness has been taken away. And so now the response follows the seismic property, the rock property, rather than the thickness change. What's actually happening here, you see it here on the right-hand well. This is the up-dip well. You're looking at the seismic response overlaid, the amplitude average there in green, the V-shale there. If we calibrate here, it would mistie here because of the tuning response affecting the amplitudes. When we detune it, it gets rid of that brightness and it moves that line over here. What effect does it see on the tuning response? That's the up-dip well. It's close to the 100% line. The down-dip well is further away from that line, but its absolute brightness is brighter because of the thickness effect. The ratio of that to that is 70%. The ratio of that to that is close to 100%. When we detune, we effectively normalize that curve and everything gets adjusted to look like this. So now the absolute amplitude also gives us the net to gross. Another example here, Yorkfield, Greater York. This is UK southern gas basin targets, detuning. So Yorkfield sits here, Rough is here. This is the thickness map, time thickness. So it's fairly thick over here, very thin over here. This is the amplitude map. And what was being proposed was that these were potential exploration targets showing gas effects. But the problem with that is that if this is a gas effect, why don't we see it here and here? And the answer is thickness. If we detune this map, the thickness effect is removed. And now you see that these are very bright and very continuous. These are no brighter. They may be gas, but they don't look as appealing as these discovery fields do here. There's a northern extension here that's also been drilled. So this looks like high risk. This looks like a much better amplitude indicator now that we've detuned it. And then I'll show you one final example with DHIs, fluid effects. Fluid effects here. So if that's a brine response as a function of thickness in a soft gas sand, the fluid effect would boost the amplitude up here, very bright. It would be a soft response, it would be brightening it. But I want to just show you something here. When it's very thick, the effect of gas is not to brighten this vertically, because with gas in there, the velocity changes, so the thickness changes as well. So the vector goes sideways. So when it's a thick reservoir, it doesn't brighten as much as you would expect. When it's a thin reservoir, it brightens spectacularly because it goes into tuning. So it may be that on a thick reservoir, the gas response is not as big as you expect because it's got more interval in which the thickness effect becomes more pronounced. And so it mutes the gas response. So you might see a DHI in a thick reservoir that's not as big as you might expect from simple rock physics. If you detune it, of course, they all end up with the same vertical response because that's the rock property effect. Hard sand oil response would be the opposite. But I want to show you a nice little example here about how you can be fooled by amplitudes on what's something which actually could be a drilling hazard in this case. So this is a very shallow example in the Netherlands, in the Dutch sector of the Netherlands. And gas here could be a gas hazard. So what you're seeing here, there's lots of gas in the system. And what you're seeing here is what is a soft unit coming up dip. And you can see it terminating here. And it's got a brightness along here that looks like it could be a gas response. The problem with this is that if that's a gas response, and I'm seeing a gas response here, why don't I see a gas response in the middle of it here? Now I can take this seismic and I can actually calculate thicknesses and amplitudes, which is what I'm showing here. This is time thickness of each unit and amplitude from the relative impedance. And I can cross plot them. So here's your classic tuning response. This feature here sticks out the side of the cross plot. And I'm going to highlight this feature here. When I do that, it turns out it's this stuff in the middle here. Now, what is that stuff in the middle? Well, if you think back to the model I showed you, if I had a brine sand here and it was gas charged, it would be thick and it would go this way out the side of that model. And that's what I think I'm seeing here. This is probably gas charged all the way through here. And this doesn't look bright because it's thickening. So there's a little local inflection, there's a little local thickening. So when I take this response and I detune it, you can see now, in fact, there's quite a noticeable brightening through here. And this is probably dimming up here because it's actually very thin. And so you're losing the response with thinning as you go up here. Eventually, you can't do anything about it. But actually, there's probably is gas in this. And no one's actually drilled this. Could be a shallow resource, but it could also be a drilling hazard as well. Okay. I think that's a very good place to stop. I'm aware of time, and there may be a few questions at the end.
Thank you. You have a question, Bahram?
Yes, we have one question. Okay, Islam asks, since both seismic tuning effects and direct hydrocarbon indicators can manifest as high amplitude anomalies, what criteria or techniques can be used to distinguish between them?
Well, detuning is the criteria to remove the effects. And you can see when I show these two maps here, when you go from this map to this one, you see a big change in the amplitudes because you've removed the thickness effect. So if you have a fluid effect and you remove the amplitude, the thickness effect, then you'll see fluid effect. So that was a good example shown down this one here. I mean, this has a gas effect. These fields are gas fields and they have a very big gas effect, but you don't see it compared to the tuning effect over here until you remove the thickness effect. And then you can see that these are bright and they're very continuous. So this would now give you much more confidence. I mean, these are drilled. So we know they're gas fields, but up here, but you can see how continuous and solid the colors are in here compared to what we see over here. This looks like there might be some residual gas, but it doesn't look very prospective. These look like really good continuous targets for drilling. So
Yes.
detuning is the answer to that.
Thank you so much. Okay, we're done with the question. If Mr. Muhammad, do you want to say something?
Yeah, actually, I'd like to thank you actually so much for this informative presentation. Actually, I learned so much a lot. myself. And I hope all the fresh graduates from Egypt got benefits from this presentation as well. And on behalf of the Amal Management and EGS, we would like to thank you so much about this presentation and for accepting the invitation. I think this will not be the last time to invite you for such brilliant presentations. I
Thank you very
appreciate
much.
it.
I
Really,
appreciate
thank
it.
you.
I appreciate your kind
Thank
words.
you.
Thank you.
Thank you so
Thank
much. It
you.
was a pleasure having you with us today.
Thank
I
you.
hope you're still enjoying fishing as well.
Yeah.
Okay, thank you so much. I appreciate it. And
You're welcome.
if we have any other questions, we'll share it with you later,
Okay.
and we will receive the answers from you.
Okay, that's fine. Well, thank you very much for the invitation. It's been
you.
a pleasure, and I hope that people have found something useful out of it.
Thanks a lot.
Of course, yeah.
You're welcome. Enjoy the rest of your evening.
Thank you.
Thank
Thanks for
you.
the team, the IT moderator. Thank you all. Thanks for the students.
You are welcome.
Thank you.
More than welcome.
Thank you.
Thank you
Have a
very
good
much,
night.
and good night.